We've already taught AI how to write poetry, how to create incredible art. But what happens when we give that code a body? That's what we're diving into today. This amazing world of physical AI, where algorithms are actually learning to walk and touch and interact with the world around us. And believe me, this isn't science fiction anymore. This is the next frontier.
For the longest time, our relationship with AI has been through screens, right? Through our keyboards. It's this ghost in the machine, living in the cloud on our phones. But what happens when that intelligence breaks free? What happens when it learns to move, to feel, to actually interact with our physical world?
And that question brings us right to the heart of it: physical AI. So what is it? Well, to put it simply, it's the fusion of really advanced AI with a physical system, like a robot. It's all about taking the incredible brain power of these algorithms and wiring it directly into motors, sensors, and limbs. This lets a machine perceive and act in the real world, not just as a passive tool, but as an active agent.
Now, building a machine that can actually do all this, especially one that's shaped like a person, it's a monumental challenge. You can't just wing it. You need a map. You need a guide. You really need a blueprint for building the future.
And this is the really big breakthrough. What used to be the secret knowledge of a few elite labs is now becoming a structured, understandable engineering discipline. We're talking about comprehensive textbooks, open source frameworks, things that lay out a clear, repeatable blueprint for anyone to build these complex systems. So, this blueprint, it's built on a few core disciplines. You start with the basics of humanoid robotics and AI concepts. Then you get into how these machines actually see the world through sensors, the specific algorithms that act as their brain, and finally, the control systems that let them move. For our little journey today, we're going to focus on the three most important steps: perceiving, thinking, and acting. Okay, so let's start at the very beginning of that process. Before a robot can do anything at all, it has to understand the world around it. It has to go from just raw data from a sensor to actually making sense of it all. And this is where it gets absolutely fascinating, because the parallels to our own bodies are just uncanny. Think about it. We have senses, right? Sight, hearing, touch. A robot has a whole suite of sensor systems: cameras, microphones, tactile sensors. Our brains process all those signals to create a picture of reality. Well, a robot uses perception algorithms and data interpretation to do the exact same thing. It's all about building an accurate internal model of the outside world. But of course, just seeing the world isn't enough, is it? I mean, a camera can snap a picture, but it can't decide what to do with that information. The machine doesn't just need eyes, it needs a brain to make sense of everything it's seeing. And this, right here, is where the AI and physical AI truly earns its keep. And forget the kind of AI that just writes an email for you. This is a whole different beast. We're talking about machine learning models that are custom built for physical tasks, and AI algorithms designed for the kind of split-second, real-time decisions you have to make when you're navigating our chaotic, unpredictable world. Okay, so our robot can see and it can think. Now for the final and absolutely crucial step: bringing that machine to life by turning all those digital decisions into actual, physical movement. The best way to think about this next piece is to imagine it's the robot's central nervous system. It's that super complex, high-speed network that connects the brain's commands to every single muscle, every motor, every joint, every little actuator in its body. The technical name for this system is the control architecture, and it's literally the bridge between thought and action. It's this whole integrated system of software and hardware that translates a high-level command from the AI, like, "Hey, pick up that cup," into thousands of tiny, precise, coordinated electrical signals that control its balance, its grip strength, and the path of its arm, all to get the job done perfectly. So that's how it all comes together, in this continuous, never-ending loop. The robot perceives the world with its sensors, it thinks about what to do next with its specialized AI, and then it acts on that decision using its control architecture. And that action changes the world around it, which it then perceives all over again, starting the whole cycle over. Perceive, think, act. That is the fundamental rhythm of physical intelligence. So we have the loop: perceive, think, act. But maybe the most exciting part of this whole story isn't just that these amazing robots are being built. It's that the knowledge of how to build them is becoming accessible to pretty much everyone. And that, right there, is the key takeaway. Building these sophisticated humanoid robots is moving out of the world of science fiction and into the world of practical, hands-on engineering. The mysteries are being replaced by textbooks, and the huge theoretical problems are being solved with open source code that anyone can download.
I mean, think about the toolkit an aspiring roboticist has today. We're talking these incredible, comprehensive textbooks that lay out the whole blueprint for you, practical labs to test out the theories, real-world code examples to learn from, and these amazingly powerful open-source platforms like ROS2, the robot operating system. This is basically the democratization of robot development.
Which leaves us with one final and kind of fascinating question. For the very first time in human history, the blueprint for creating intelligent physical beings is becoming widely available. The tools are here, the knowledge is accessible, so the only real question left is, with this power, what will we, as a generation of creators and engineers, choose to build?